So the reaction of the alkenes are continued, and this one is hydration, which is addition of water. So a water molecule can be added to an alkene, and such a reaction is called the hydration reaction. And similar to the addition of hydrogen or addition of hydrogen halide, the double bond between the two carbons will be broken into single bond, and the hydrogen of the water molecule will go to one carbon, and the hydroxyl group or the OH will go to the other carbon. Important point to note that a strong acid is required for this hydration reaction as a catalyst. Otherwise, this reaction will not occur, and the product that will be formed is an alcohol. As it was there in the previous slide as well, that a strong acid is required for the reaction. If only water is added to the alkenes, no reaction will take place. So with only water, the reaction does not occur, but when a small amount of acid is present, only then this hydration will take place, and it is usually required in small quantities, as mentioned here as the word trace, which also means in a very small quantity. Next up is the alkene propene, the three carbon alkene, and its reaction with the water known as hydration. And for such a reaction, Markovnikov's rule that we studied in the previous lecture will be applied here as well. So the hydrogen will go to the carbon with more hydrogens, which has got more hydrogens already attached with it. So when we look at this double bond, the carbon on the right side has got two hydrogens, whereas the one on the left has only one. So according to the Markovnikov's rule, the hydrogen of water will be added to the carbon that has got more hydrogens already present, and the hydroxyl group will go to the other carbon. So this will result in this product at the top, which is known as 2-propanol, in which the hydroxyl group is attached with the second carbon. And the opposite way around, that the hydrogen goes to the second carbon and the hydroxyl goes to the first carbon. Such a product, that is 1-propanol, is not observed at all. So this one totally follows the Markovnikov's rule. Second example also has got a cyclohexene, in which the water molecule has to be added, and the same Markovnikov's rule is going to be applied. This carbon in the double bond has got more hydrogens than this carbon. As we can see, an additional hydrogen is attached here. So the H will be bonded to this carbon, as we see here. The hydrogen has been attached here, and the hydroxyl group attaches to the carbon which had less hydrogen atoms in it before the reaction. Next are a few examples of the alkene reactions in which you have to predict the major product of the reaction, and also name the alkene, reactant, and the product, include using the IUPAC nomenclature. So let's go with the first example, which is a 2-carbon alkene, and the hydrogen gas is going to be added to this one. So this is a symmetric reaction. One hydrogen goes to this carbon, the second hydrogen goes to the other carbon, and there is always going to be only one product. Same is the case with the example C. It's a bromine halogenation reaction. One bromine will be added to one carbon on the butene molecule in this case, and the second bromine will go to the other carbon, and the double bond will be converted or broken into the single bond. Whereas in B and D we have to apply the Markovnikov's rule, and in this case, or the B example, the hydrogen, according to Markovnikov's rule, goes to the carbon which had more hydrogens present before the reaction. So this is the one, it had one hydrogen. This carbon do not have any hydrogen. So the hydroxyl or the OH of the water molecule will go to the carbon with lower hydrogens that were present, which is this one in this case. Similar is the example of hydrogen chloride, which is an example of hydrogen halide, and the hydrogen in this case goes to the carbon that had more hydrogen, which is this one. It had two hydrogens. The second one will take up the chlorine atom, which had only one hydrogen, and the double bond again is converted into a single bond. So you have to write down their formulas, and you have to write down their names as an homework. Do it, and you have to send these on my email address, which is there in the syllabus, and everyone has to do it, all of these. Next are polymers of alkene. So what are polymers? Polymers are defined as the macromolecules. Do remember the word, it's macro, which means big, not micro that we usually hear, which means small. So these polymers are macromolecules, means they are big molecules composed of repeating units, and those repeating units will be called monomer units. So we take hundreds or thousands of these monomer units, join them together, and we get the polymer. As written here, thousands of these monomers can be present in one polymer. And many commercially important materials are actually addition polymers made from alkenes and substituted alkenes. So we take alkenes and substituted alkenes and add them together. That is why they are known as addition polymers. So this is a sequential addition of the repeating alkene monomer unit that will result in addition polymers. In the reaction, it is shown an alkene polymer as a reactant on the left side, and the double bond clarifies that it is an alkene, whereas these R groups can be hydrogen, they can be a halogen molecule, or they can be alkyl group. Some catalyst will be required for such reaction, like heat or pressure, and thousands of these alkenes will join together and give us the product addition polymer. Here are some examples of these polymers of alkenes that are used commercially, and you have to remember the name of the monomer unit, the polymer that it forms, and its uses in the industry. So first up is styrene, and the polymer that it will make is simply polystyrene, and it is used in the styrofoam containers. Those white colored cups that you usually use for drinking coffee or tea, they are made up of this styrofoam. Next is acrylonitrile, and the polymer is polyacrylonitrile, also known as orlone, and this material is used for clothing. Next is methyl methacrylate, and the polymer unit is polymethyl methacrylate, also known as a leucite, and this one is usually used in basketball backboards. Then is the very common product of vinyl chloride, the monomer unit. It's polymer polyvinyl chloride, shortened as PVC, and plastic pipes, credit cards, toys for children. This PVC makes up a lot of materials commercially. And the last one is tetrafluoroethene, which will make a polymer polytetrafluoroethylene, and also known as, or shortened as, Teflon. and this one gives us non-stick services and is usually used for the cooking pans or any such utensils that are used in the kitchen for cooking. So it provides a non-stick surface that the food will not stick to it. Next are alkyne reactions, and to begin with, the first one is hydration of alkynes, so which is the addition of water to the alkynes. Alkynes are the hydrocarbons which have the triple bond in them. So here is a typical alkyne, and when water is added to it, its triple bond will be converted into the double bond first, and one carbon will take a hydrogen of water, and the other carbon will take the hydroxyl group, and this product that is formed first is known as enol. So this is known as initial product, and it is not stable. This enol is a mixture of alkene and an alcohol, and this product will be rapidly isomerized, so it will be converted into another product which will be known as the final product. And there are two possibilities for the final product. It can be an aldehyde or it can be a ketone. If the R dash group initially here in the alkyne, if it was a hydrogen, then the end product will be aldehyde, and if the R group was a alkyl group, then the final product will be a ketone molecule. So as we saw in the previous slide as well, that the enol is not stable molecule. It is going to be rapidly converted into either ketone or an aldehyde. So in this case, this is the R group which corresponds, or which is on the end where the hydroxyl ion or the OH ion is going to be added up. This one is the R dash group. So when the R dash group is an alkyl, as in this case it is an alkyl, the enol is converted into the ketone molecule. It isomerizes, or another term used for this reaction is tautomerization, into a more stable product. Next is hydrogen of the alkynes, and it is similar to the hydrogenation of alkenes that we saw. So the reaction here, we have a typical alkyne, and the hydrogen or H2 is going to be added, so the triple bond is going to get converted into the double bond. One hydrogen is added to each carbon of these, and catalysts are required for this reaction, which can be platinum, plutonium, nickel, or RH. And this alkene that is going to be formed is known as an intermediate. Why is it called an intermediate? Because this reaction shown is something we call a partial hydrogenation. If plenty of catalyst is available, this alkene will be converted into an alkyne eventually. More hydrogens will be added up to it, and it will be converted into alkynes. But if we have limited catalyst, then these alkynes can be used to prepare alkenes. If the catalyst were available that is active enough to catalyze only hydrogenation of the alkynes, but not active enough for the hydrogenation of alkenes. So it's the concentration of the catalyst or their activation basically which determines that whether we get a alkene or whether we are going to get an alkane as the final product. If the reaction stops at alkene, we call this partial hydrogenation of the alkyne. And now there is a special catalyst known as a Lindlar's catalyst that limits the addition of hydrogen to an alkane to 1 mole and produces a cis alkene. So what this catalyst does is that it catalyzes the hydrogenation of alkynes to alkenes, but stops the reaction there. So it does not go further, and it will not catalyze the reaction from alkenes to alkanes. So this catalyst is basically used when we have to do partial hydrogenation of an alkyne, and this Lindlar catalyst consists of palladium supported on calcium carbonate. So its composition is important, and this has been poisoned with lead acetate and quinolone, two products. So this one is known as synhydrogenation, and it will result in cis alkanes as the product, and that will be the product where the reaction stops. So it will not go further into the alkane molecule. It will be partial hydrogenation in the presence of Lindlar's catalyst. So here is a actual example of the hydrogenation of alkynes. We have got a 2-pentyne molecule which has got a triple bond in it. This triple bond will be broken down to double bond in the presence of hydrogen and the Lindlar catalyst. And as we saw in the previous slide, Lindlar catalyst is the palladium plus calcium carbonate. That is its composition. So one hydrogen will be added to each carbon atom, and this will result in a pentene from the pentyne, and this will be a cis molecule. So cis 2-pentene is the product of this partial hydrogenation in the presence of Lindlar catalyst. Next reaction is the addition of hydrogen halide to alkynes, which will follow the Markovnikov's rule that we studied earlier. So here is an alkyne with a triple bond, and the HBr molecule, the hydrogen halide, that has to be added to it. So the Markovnikov's rule stated that the hydrogen goes to the carbon which has more hydrogens. This one has one hydrogen, this one has no hydrogen. So the bromine molecule will be added to the other carbon, and we can see the product, this carbon with after the addition of hydrogen, and this one takes up the bromine. Now this alkene that is formed can be converted into an alkane if enough HBr is present, and the same thing will result that this hydrogen again will be added up to this carbon, whereas the bromine will be added to this carbon according to the Markovnikov's rule. Next reaction is the addition of halogens to alkanes, and this is an example of the symmetrical reactions. So first example is ethine reacting with the bromine, which is the halogen, and ethine is first converted into ethene, which is 1,2-dibromoethene. As I said, this one is a symmetrical reaction. So one bromine is added to each carbon. Basically, the triple bond is going to be converted into a double bond, as we can see here. In presence of enough bromine, this will continue, and this dibromoethene will be converted into tetrabromoethane. So this double bond will be broken into the single bond, and it will take up two more bromines, again one carbon each in this case, and this will result in a product known as 1122 tetrabromoethane, as it has got four bromines added to it. The second example is for the propene, the 3-carbon alkyne, propine, sorry, the 3-carbon alkyne with the triple bond, and its addition to the chlorine molecule. And the final product is going to be a tetrachloropropane in this case. So this will be 1122 tetrachloroethane, tetrachloropropane. Next up is a big table of the functional groups, and most of these you have to memorize. A question can be there in the exam, so you need to know the type of the compound and the functional group. These two columns are absolutely important to remember, and also remember the structural formula. So the first 3 columns you have to remember. If you can remember or memorize one of the examples as well, that will be additional benefit. So in the alcohols, the functional group found is a hydroxyl group, and the formula, basic stuff you should already know. It is OH. For the aldehyde, again very important compound, and the functional group is known as carbonyl group, which is CHO, one carbon, one hydrogen, and one oxygen. In the amide compounds, the functional group is carboxyamide, and the formula is CONH2. Amine are contain the functional group amino group, which is very important, NH2. Carboxylic acids usually have the carboxylic groups, COOH, like the acetic acid, the very common example for this one. Esters have ester group, ethers have ether group, and halides have halogen atom. So this is fairly simple, you don't even need to memorize. Ketone are very important, in which the functional group is known as carbonyl group, and it is the COR group. And acetone is a typical example for this. Ketones, for the alkenes, we already discussed for such a long time. It has the double bond present. Alkynes have the triple bond present. Any example of the alkenes or alkynes can be there: propene, propyne, butene, butine, and so on. So here are a few examples. After memorizing the functional groups on the previous page, you have to name the functional groups present in these formulas, and they can be there in the exam. Which one of the following functional group is present in this compound? You simply have to check the functional group, which in this case is the hydroxyl group. So this one is an alcohol. The second one has an amino group, this one has an aldehyde group, and so on. Uh, and the rest of these you can do yourself. Try to memorize the table first, and then try to answer these, rather than just going back and checking these names. This slide is really important for the exam point of view, as such a question can be there. And here the last slide, the question is, what are the functional groups found in these molecules? So these molecules have got more than one functional group present, and you have to find out all of them and name them as well. So this first one is an artificial sweetener, which is usually found in every house, or most of the houses that we use in place of the sugar to sweeten our coffee or tea usually. So this one has got this NH2, or the amino group present. Apart from that, there is a double bond present as well, plus the COOH, which is the carboxyl group right here. And this whole group, which is carbon double bonded with the oxygen, along with the other oxygen and CH3, this is known as the ester group. So these are a few groups present in this artificial sweetener. Second up is Tylenol, and this Tylenol, also known as acetaminophen, is a common drug used to lower the fever basically. And the two groups found in this one is the hydroxyl group, the OH, and the carboxyamide group present, this big one right here. Last is atorvastatin, again a drug used in medicine to lower the blood cholesterol levels. So this one is a commonly used drug as well, and again it has got plenty of groups present in it. The COOH group, which is the carboxyl group, hydroxyl groups are there, double bonds are found, and the halogen atom, like fluorine, is also present in this one.